So IMOD, in a river cross-section drain and catchment whose area is 12-14 square kilometers, the river flow data have been observed at hourly time step for a period of 1 year. At the same time, precipitation and potential evapotranspiration have been estimated. The related observations can be downloaded at the web addresses that you see here, and you can download it very quickly if we go back to my web page. And here there is a link for river flow data, and there is a link for rainfall and evapotranspiration. So let's click on rainfall and evapotranspiration. What happens here is that there are two columns. These are hourly data. The first column is rainfall, so there are zeros, it's hourly rainfall. The second column is potential evapotranspiration. I suggest that you download the file. In order to download it, I suggest you to go back to the page, go back to the link, and click with the right, save as, save file as, something like that. I do it, I save it on my desktop. Good. And then let's click on river flow data. And you see here that there is the specification that this is river flow, river discharge in cubic meters per second. Again, let's download it. Good. Oops, I downloaded the wrong one, sorry. Good. Now, let's go back to the PDF. So, the exercise requires that by using the above data set, the IMOD model should be calibrated by using sum of squares as objective function. The initial value of the river flow is set to 15 cubic meters per second. This is initial value, meaning that it's the value of the river flow at time 0. We will see how to use this information. A comparison should be made by using the sum of absolute errors as objective function. Furthermore, model validation should be performed by calibrating the model of the first 6 months of data and verifying the model by using the last 6 months. And forget about explaining a brief report the above elaborations with the required graphs. I'm not requiring this for the current year. I'll explain you later what I'm requiring. An example code can be downloaded at the usual link on my web page. So let's have a look at the R code of the IMOD model, so we see what it is suggested. This is the code. It's quite short. If you scroll down, you see that it's not long. So basically, what is the purpose of this exercise? First is to learn new features of R, because you see that here it starts by saying IMOD equal to function. We don't know yet how to write a function in R, so we have to learn this, and I need to explain to you why this is the solution that I prefer to use this today. And then there is the code of IMOD. This is a suggested code for IMOD, and I think this is the most advisable way forward, because if we start writing a code, which is in principle possible, without looking at this example, I think it would take a lot of time. It is in principle possible. You already have the knowledge that may allow you to write the code autonomously, independently of this suggestion, but it would take some time. So I prefer, in order to optimize our time, that we follow this code, but we try to understand what's done here. I tell you, I'm not sure that this code, which is something that is also available on the web, is the most efficient solution. There might be more efficient solutions than what I'm proposing here. And this works because it's tested, but maybe that if you decided to write it independently, maybe that you found more efficient efficient solutions. This is possible. This is a suggestion that we use as a first guideline for writing a code, writing a function. But I really want to stimulate you to think about what you are doing, to think of this code, how it works. I would like to stimulate you to wonder whether the code is efficient, whether there are other solutions. This would be great, okay? Because the risk that it's entailed in using this way of teaching, proposing an example, is that the student takes it and doesn't elaborate on what we are doing. It is strongly needed that you elaborate. Okay, but I will also give you some more suggestions in order to do that. And then, with this code allows to run IMOD one time for given values of parameters, as we will see, meaning that if you have a set of parameter values, a vector, you remember that IMOD counts 5 parameters. You give the value of these parameters to this routine, and the routine gives back the simulation. But we have to do much more. We have to calibrate IMOD. So we need to do something more besides writing the algorithm. Furthermore, it is also required that we try to validate it. We will not have the time to do everything together. As I'm not requiring anything to be delivered at the exam for this exercise, it's not absolutely a problem if you decide not to move further on after the closure of our cooperation, meaning that I think that we will be able to get to calibration, no more. If you want to move forward, and maybe you want to present with a few slides what you did in the next lectures, this is perfect. Otherwise, as I said, I will not require to do anything more, so it's up to you. This is an opportunity for interaction. I really would like that you made something like moving forward and then presenting the results of validation, presenting the results of some experiments that you may make, like what happens if I change this parameter, if I change the other parameter. And once that you have the code written, it's relatively easy to move forward. Okay, but this is up to you. We will have time to discuss further. There is another thing that I wanted to tell you about interaction. And we studied together ray for and off modeling, and in particular we studied the linear reservoir and IMOD. Ray for and off modeling, we said it's very important for sustainable design of water resource systems because it gives an opportunity to estimate water resources availability. Keep in mind that ray for and off modeling is also used for designing hydropower plants, in particular small hydropower plants, because it gives an idea of the amount of energy that we can retrieve from a hypothetical plant, which is directly related, the amount of energy, to water resources availability. So ray for and off modeling is extremely important. We just started a couple of models, linear reservoir and IMOD. There are several other options for making ray for and off modeling. In particular, there is a class of models which is I think interesting and could be the opportunity for you to deliver a presentation to the class in the month of May. And these are the spatially distributed ray for and off models. It is written, I hope that everybody can read if I write here. Spatially, I forgot to turn it off, sorry. Okay. Good. Spatially distributed rainfall runoff models. Okay, so it's very easy to find information on the web. The only problem is that you find probably too much. If you want to deliver a presentation with 5, 8, 10, max 10 slides on this. Very good. And if you need any information, any help from me, just contact me by email or directly when we meet. Perfect. There is another thing that you could do. Besides delivering a presentation, or instead of delivering a presentation, you could propose to me, this is a bit more difficult but possible, an extension on my web page dedicated to iMod, to train for and off modeling. There is already something on spatial distributed models, I think, but it's very short. Let me check. And it is very short, and it's just 1 second. I think under deductive methods, let's see, spatially, no, there is nothing, let me see, distributed. Okay, there is a mention here, lumped versus distributed, but I'm not sure if there is some more. No, there is nothing more. So, rational formula, iMod, groundwater, okay. I think after iMod one could include here a section with spatial distributed models. This is something that if you are keen on doing that, I'm keen on supporting you. And of course you will need some help from me. Just contact me if you want to do this, and then we can present together to the class the development. This would be something that I think it is interesting to do. Okay, now let's move forward. I suggest that the first thing that we do is to open an R console, and if you want to use RStudio, it's perfectly fine. And let's upload the data. This is the first issue. I think you already have the means to upload it, you know how to do it, but as usual it will be not straightforward. So let's upload this data. One thing that you have to check is how many lines you have to skip. So let's have a look at these files. These files are, one is discharge sint, extension txt. If we look at it, we see that there are 2 lines that we need to skip. Good. Let's look at the rain evapotranspiration. There are 3 lines that we need to skip. This is an information that it's important. Okay, now let's open our R window. Just 1 second that I enlarge the font. Otherwise, it's difficult for you to read. Let's try with 18. Okay, I clear the screen. Okay, now we can, as usual, write river flow equal to scan, and I don't remember the name of the file, discharge syntax.txt, skip equal 3. If I will remember, let me check again because I don't remember. No, skip equal 2, sorry. Okay, this is the result. Everything it was uploaded. And we see that it's correct because it says that it read 8,760 items. Of course, you need to put the path, etc. on the desktop, if you say it on the desktop, etc. Everything is okay? Are you still working? It seems yes, so I wait a little bit. Sorry?
You have to save the foundation of the file.
Yeah, but wherever you want. If you decide to save on the desktop, then you need to give the path of the desktop to the program. And you have two possibilities. Either you tell R that your working directory is the desktop, but yeah, this is a possibility. And the other possibility is that you give the full path in the scan instruction. If you don't succeed, then I will help you. If you just look in the room, there is text for an exercise on my web page, and I added one link in the web page for the today's exercise. You can look at my, okay, perfect.
Sorry.
Yeah.
There is not on this, but about the linear reservoir exercise that you put like 2 weeks ago, maybe 3. Is it because I tried to do it, but I think I didn't succeed. Is it possible to upload like a script of RStudio about the linear reservoir for that specific exercise?
I think we did, just I need to remember, we did it together up to what stage?
For the linear reservoir?
We didn't do anything together.
No.
And, but in the previous exercise, okay, I understand. Ah, yeah, for the linear reservoir, I told you to try independently. Yeah, okay. I see your point. I think, yeah, I could do it, but the problem is that, okay, let me think at it. Maybe the next exercise we can go back to your questions on that. Okay? Perfect. Did you succeed in uploading the data? And what about you? Sorry, let me see. Did you upload the data or set? Okay. Let me see. Okay. It gives an error or what? Let's see. rainfall and evapotranspiration, similar procedure. But let's use a name that puts in evidence that it's a temporary file. It's temporary because rainfall and evapotranspiration are in the same file. We need to separate. We need, first of all, to upload the file and then separate them. Okay, so let's see. Skip equal 3 this time. And you see that it was successful in reading twice 8,760. Okay, good. Now the problem is that we need to separate this data, because if we look at the vector that we uploaded, like 110, you see that we have one data that refers to rainfall, plus one that refers to evapotranspiration, again one of rainfall, and etc. We need to separate them. Can I check if you succeeded in uploading? Everybody uploaded it? Okay, now we need to separate them. So, first, in order to separate them, we need to transform this vector into a matrix. So let's write temp equal array temp dim equal C 28760. Good. And then we can write rain equal temp 1 comma and evapo equal temp 2 comma. Let me check if everything works out well. Yeah, everything works out well. Okay, do this. So be aware of the check that I made. Basically, what I did was to transform the vector in a matrix, as I said, and to pick up rain as the first column of the matrix and evapotranspiration as the second column. But I checked by displaying the first 10 observations of rain and evapotranspiration. I checked whether or not I did correctly, because the risk here is to make a mismatch. The risk is that you call rain what is evapotranspiration, and vice versa. The risk is that we still mix rain and evapotranspiration data. It is important, in order to correctly separate them, that the dimension of the matrix is well specified. In this case, everything was correct, but when you do these kind of operations, please check. Let me close the door. Okay, much better. Any problem?
But if we do this kind of operation in Excel, it's fine.
Yes, I think it's longer, but probably it takes longer. But anyway, it's fine. In Excel you have to upload the matrix, the file, and then you have to separate the columns, save the columns as a text file, and then upload in R. Yeah, it's fine. I'm sure that it takes longer. Okay. Problems? Everybody's online? Good. Now we have the data, and another check that we could find is just try to plot them. Plot river flow. Sorry. River flow, type, equal line. Just to see, just to have a look that everything is fine. It seems that indeed it's okay. Let's try to plot now the rainfall data. Good. And evapotranspiration. Good. Evapotranspiration has this shape because it was computed here by adopting standard values for temperature in the different months. So it's a monthly value for temperature, so it remains constant evapotranspiration during the months. Okay, this is fine. Okay, now we are ready to start. In order to start, we need to write a code for iMod. And in order to do that, let me open a text editor. You remember we decided when we write codes that we agreed that it's better to work on a text editor instead of working directly in R. So let's take a text editor as you prefer. I take one that is available under Linux, but you of course can make whatever choice you like. I just need to change the font. Let me see. Okay, good. Now, in order to apply iMod, remember that our first target is to apply the model for a given parameter vector. We could write a sequence of instructions. This sequence of instruction, what has to do? Remember, we have 8,760 observations of rainfall and the same number of estimated evapotranspiration, potential evapotranspiration. If we adopt a guess value for parameters, we have everything we need to apply iMod. River flow it's also available, but it's not necessary to run iMod. It's necessary only if we want to test the performances of iMod. So let's concentrate now on what we need: rainfall and potential evapotranspiration. It's available. Okay, so we can apply iMod. And what do we have to do in order to apply iMod? We have to eventually start from the first time step, look at rainfall. If there is no rainfall, nothing happens. When there is rainfall, we have to compute the variables, the iMod variables that allow us to estimate the river flow in detail. When it starts raining, we have to compute CT. Remember that we said that CT is water stored from the beginning of our simulation in the areas that are not saturated in the catchment. This water stored in these areas that are not saturated increases for rainfall, decreases for evapotranspiration. When we introduced I mod, we first assumed that evapotranspiration is 0 because it made our life easier. Now we have to account for it. And therefore, again, CT increases by rainfall, decreases by evapotranspiration. So at each time step, what we have to do is to look if it rains or not. If it rains, we have to compute C at the same time step. We have to compute evapotranspiration at the same time step. And then we have to compute W, which is the storage into the catchment. The storage into the catchment is different with respect to CT because it's generally lower, because there are in the catchment saturated areas that cannot store water anymore. While CT can continue to increase because we refer to non-saturated areas, the storage into the catchment includes water that is stored in areas that are already saturated. So WT is different from CT. I hope you can follow me. If you have difficulties, problems with following me today, you need to look back at the theory. And then once that we estimated CT and WT, we have everything we need to calculate the contribution to river flow, which is formed by two separate contributions, as you may remember. We will review them now. So we have to set up an algorithm, a sequence of instructions in R that allow us to make these computations. Okay? Of course, this computation is to be repeated for each time step. So we will need a 4th cycle. At some point into the algorithm, we will need to set up a 4th cycle. Good. Another thing that we have to keep in mind when we move forward with practical computation is the units. We have to be very careful about the units because we have rainfall and evapotranspiration in millimeters per hour. We want river flow in cubic meters per second. So beware of the units. Okay. One more consideration. We could, as I said, write a sequence of instructions to run IMOD. This is fine, but it is, when you have something, a code that needs to be repeated several times, it may be more convenient to write a function in R. A function like the functions that we already know. We know that there are functions in R, like mean, like SD for standard deviation, like SQRT, square root. We learned that these functions are embedded in R already. We don't need to write them down. They are already available. And we know that they have arguments. And we know that they give back a response. So why not writing a function that has argument, the parameter vector of IMOD, and gives back the simulated river flow. So you may ask me, what is the advantage of doing that? The advantage is basically that you have a code that runs through only one instruction, not 100 whatever lines, not 100 instructions, but just one. So your history keeps cleaner. This is the first advantage. The second advantage is that if you run a function in R, any variable that is defined inside the function is not stored in your memory. It is cancelled when the function finishes the computation. What is the advantage? That you keep your memory clean. When you look at the list of variables through the ls function, you don't see all the variables that you defined into the function, which is a considerable advantage because your space, disk space occupied in the PC when you save is lower, and more important, your memory is cleaner, which means that if you have to look for variables, if you have to get back some variables, it's more convenient if you keep the memory cleaner. Of course, you have to be aware that any variable that you define into the function is removed at the end of the computation. So, if you have variables that you are interested in storing, you have to tell the function, please store this, save it. But otherwise, writing a function is much more convenient. Okay, so let's learn how to write a function. And my suggestion is, not my suggestion, what you have to do is to first define the name, like imod, equal to function. This is the function that allows you to define a function. Function, and then you have to give the arguments. Okay, let's say that the argument is a vector called par. Okay, now we need to follow up with all the instructions that we need to run imod. So you see that there is no much difference. There is only